Hi guys, welcome to lecture 10, Kinetic and Gravitational Energy. Here you're learning attention and success criteria. Please complete the KS table. Pause the video while you complete this. Okay, so having a look through here, we can see that we need to understand conservation of mechanical energy. We want to be able to interpret the story of energy time graphs. And going through here, we see a little bit more heavily on the skills part of the verbs. So in terms of knowledge, well, we need to know what is conservation of mechanical energy. Secondly, what are some formulas in order to be able to do kinetic and gravitational energy calculations. And then finally, what's an energy time graph? And so our skills should be, well, can you do these calculations? And secondly, can you read this graph? So, in a previous lecture, we looked at types of energy leading to the idea of work being the change of an energy. And the two energy types we're looking at through this unit will be kinetic and gravitational, and these will fall under the idea of mechanical energy. And secondly, well, we need to remember that this idea that work is the change of energy. So if something's asking what's the work, well, we need to look at the energy. So if we know kinetic energy before and after, that means there must be some work done. If we know the potential energy before and after, there was some work done. So these things are related to each other. We're going to look at systems involving changes of both these. So let's start with kinetic energy. Now the textbook has a good algebraic way to derive equations for kinetic energy. You don't need to memorize this, it's worth a read over though, and it may help you understand a bit of the background. In fact, if you look at the work equation, for work equals force times displacement, and you look at the kinetic energy equation and you think about some of the calculus you might be learning about now in specialist mathematics, you might sort of pick up a little bit of similarity there. Okay, so kinetic energy obviously depends on how fast something is going. Slightly less obvious though is that it also depends on its mass, and that's why reading over that explanation for how to derive it's useful. The equation for kinetic energy is that EK equals half mv to the power of 2. And the first worked example they've given there is pretty obvious, but I do want to do the second worked example together. So here's the worked example 13.3b. Reads a 520 kilogram rocket sled at rest is propelled along the ice by an engine developing a constant thrust of 12,000 newtons over a distance of 40 meters. Assuming all the work goes into motion, calculate the following things. So I want to go through, we'll do our process. Firstly, what are the numbers? We've got a mass here, we've got a force, we've got a distance. There's this word constant. Constant is an important mathematical word, so that's going to be important to consider. And all the rest is just story. So the first question is asking us, what is the work done after that 40 meters? Notice here, work done by the engine on the sled. So it's the engine that's giving energy to the sled. This word constant tells us that we always have 12,000 newtons, so we don't need to worry about the force changing at all. It's just going to be a flat rectangle, basically. So our work will just equal F. S equals 12,000 times 40 equals 48. Yeah, 48. 4.8 times 10 to the 5 joules. Okay. Now this second sentence here is really important. Assuming all the work goes into motion. Remember, work is change in energy. What sort of energy was changing here? Work equals change in energy. Well, it's change in kinetic energy. So work equals the change in kinetic energy. Now it started at rest. So its initial kinetic energy was zero, it wasn't moving. It had zero velocity, it had zero kinetic energy. I hope I don't need to prove that. So that means all this work that's just done, this 480,000 joules of energy, now has to go into the kinetic energy. Well, we have a formula for kinetic energy, don't we? And knowing that, we can now work out the velocity. Because the second question is asking us, what is its velocity after 40 meters using the kinetic energy formula? This is really important. Sometimes you'll get questions like this that says, do it this way. one of the beauties of motion physics is that all these formulas are always true. There can be more than one way to work something out. I could take the force and the mass and work out the acceleration, take the acceleration and the distance to work out the final velocity, and that would give me the right answer. I recommend you have a go with that. But this one is specifically asking use the kinetic energy, and being as we've got this verb calculate, that would mean that on an exam we would have to show working to get the full marks, and if we didn't do it this way you would not get the full marks. You'd still get 1 mark if you got your answer correct, but you would not get any marks for your working. So be careful with that. Okay, read the question thoroughly and make sure you know what it's asking you to do. So work is changing kinetic energy. Kinetic energy equals half mv squared. So let's substitute that in. 4.8 times 10 to the power of 5 equals a half, and mass was 520 v squared. Opposite of multiplied by half is to multiply by 2, or you can think of this as divide by 2, multiply by 2. Opposite of 520 times v squared will be divide by 520, so I'll divide that over, and then square root the whole thing at the end of it to get to the square. Again, if you're having trouble with the algebra on this, you need to see me in your own time. So 2 times 4.8 times 10 to the 5, divide that by 520, take the square root of it, and that will give me v. 4.8 times 10 to the power of 5 times that by 2, divide that by 520, take the square root of that. We have here that v is approximately equal to 43 meters per second. Now, as I said, we could have done the other way, but the question is specifically asking us to use this formula. Okay, so be careful with things like that in the text. Our other type of energy is gravitational energy, and the equation for this can be derived in a very similar way, but again not necessary for your syllabus. The formula is a bit simple. Potential energy equals mass times gravitational acceleration. I will add a quick note for that. Oops, meters per second squared. Okay, so the G, remember, is the gravitational acceleration. We saw that symbol back a couple of videos, I believe in 1.5. But more accurately than this one, and the one that appears in our booklet is this, that the change in potential energy equals mg times the change in height. I'm not particularly fussed about which. This is the one that's in your formula booklet, so I'd make sure that you practice doing it that way though. And this is because we're looking at change in vertical displacement, which means that there's a change in that potential energy. Because even if you're resting on the surface of the Earth, you still have some potential energy. You are a distance away from the gravitational centre. So really what we're saying is that we're only looking at the change in potential energy, not the absolute value of the potential energy. And note that I did say that this h for height, is about vertical displacement. If an object goes up a ramp that's about 5 meters long, there's a good picture of this in your text, but only goes up by 2.5 meters in height, like on the example page 362, this 2.5 meter height is the delta h we use. It's not the 5 meters. So for this picture, if this is 5 and this is 2.5, oh, pardon me, this is delta h, okay? Not that. You could take a 10 meter long ramp, you could take a 20 meter long ramp, you could take a 500 meter long ramp. Doesn't matter. How long the ramp is doesn't matter, outside of using the angle to work out the height with a bit of trigonometry. It is just the vertical height. This is how people move gigantic stone blocks to build pyramids, because ramps allow you to spread the energy out slowly so you don't have to work so hard to lift something. And if you go, oh, well, how can you do that? You've got a lot of time, and there ain't much, not like there's any internet and TV shows to watch, so building stuff is kind of what people did. Okay, so it's the vertical height, do be careful of that. Now, something we learnt back in grade 8 is conservation of energy, that the total energy does not change. And so like momentum, those equations are important because it will give us this idea that these two things should add together to be a number that doesn't change. And we're going to do some questions that involve with this. Note, these formulas don't appear in your booklet. These ones are just derived and substituted into this. But this idea that if I increase my kinetic energy, my potential energy must fall, or vice versa. Okay, so if you're, say, dropping a ball, obviously your potential energy is going to drop, your height gets lower. But if this value is constant, well, that means that this has to go up, okay, because they have to still add up to be the same number. If this goes from 2 to 1, this will have to go from 1 to 2. And this matches what we see when we actually drop something. We drop something, the height goes lower, the GPE therefore becomes less. The kinetic energy increases because the object speeds up. Note, there is a really common misconception that people have that once an object is falling, it falls at the same speed the whole time. It does not. It accelerates at the same rate the whole way down, but the velocity continually increases. Now, for this though to be true, we cannot add or remove energy to the system. Okay, so you can't have any friction taking energy away. You can't have drag or sound losing energy from that. You can't have it glowing and giving off energy. So a lot of times you'll see these sort of questions where they'll just say, oh yeah, assume there's no friction, or assume energy is conserved. Okay, so be careful with that. So energy time graphs showing these two values, kinetic energy and gravitational energy, are a good way to demonstrate the movement of objects. And being able to describe this is one of the syllabus objectives, and so we will do some examples in class using the carts, but I want to go through one of them in the textbook. None of them in the text seem to have energy being conserved. If you look at the ones, I believe it's page 364, where you've got kinetic energy and gravitational energy in terms of a trampoline, there is a point where all the kinetic energy goes to 0 and the gravitational energy goes to 0. In fact, I think that the gravitational energy should really go to negatives because it's going below the surface of the trampoline. But again, it kind of depends on where you say your 0 is. At that point, the energy isn't lost, it's just being stored in the elastic energy, which does have an equation, but it's not in our scope, so don't worry about it popping up. But it doesn't mean it's gone anywhere, okay, or it doesn't mean it's lost. The second graph does demonstrate some energy loss because the kinetic energy doesn't go back to the same height. And I'd recommend you have a go drawing any ET graphs for anything that moves, not necessarily something that falls. Just try with the kinetic energy, going down a hill, or throwing a ball at a friend. Just think about, well, what is the kinetic energy at these points? What is the gravitational energy at these points? And I want to have a look at this one. This one here has been given to us as a response to a roller coaster. The solid line is the gravitational energy, and the dashed line is the kinetic energy. And we can see here that there's this slope across the top of total energy that continues down. Things that I can note here from this is that, well, when gravitational energy is high, kinetic energy is low. Most of you have been on a roller coaster, I imagine. At the top of the roller coaster, you've got a lot of gravitational energy, but you don't have much kinetic energy, you're not moving. You get fastest when you're at the bottom. And then as you go up higher, you slow down. So as we go up higher, we slow down. And then as we go lower, we get faster. The fact that there's this slope here tells me that there is energy loss. Energy loss from friction, which is why the very first dip is always the highest. Every other dip afterwards, every after hill afterwards, cannot be higher than the first one. If it is, the roller coaster won't work and I won't get over the top. So these sort of describing of things is really important when you are looking at energy time graphs. Okay. So in this video we have learnt the following. We have learnt basic calculations involving kinetic and gravitational energy, and we've interpreted meaning from an energy time graph. For your entrance slip to class, please complete Check Your Learning 13.3 questions 1 to 3. Submit them on the 1.10 space on eLearn. Thanks guys, and have a good night.